All right, as promised, I know you've been waiting for this for a long time, but we are going to finally prove Gauss's law. And you're just going to see how wonderful it is. I've been building it up for some time now. One video to be precise. So, as you can see here, we have this scary looking equation, and what it essentially represents is the flux through an enclosed surface. So, this little squiggly line, or an integral, with the circle represents an enclosed surface. So that enclosed surface has an electrical field. It's electrically charged, whether it be positive or negative, doesn't matter, at least right now. And this is basically the dot product of the electrical field with the area, which is also a vector, as you can see. And generally, area is not a vector, but you'll see momentarily why area is represented as such. So let's start breaking this down and derive it, and then we're going to put it to use so you can just see how amazing it is. So first we're going to just take some arbitrary shape that has a little bit of curvature, right? So we have some shape, do that, and we're going to label this shape S, right? All right, so we have this shape. It's also electrically charged, so keep that in mind. Now what we're going to do is we're going to take one of those electrical charges that's tucked deep within the surface, and by the principle of superposition, which states that the magnitude of the electrical field is independent of all the charges at which it's around. So by virtue of that, we can just take the vector sum of all of those charges. So this is entirely possible. So there's nothing fishy going on here. So we got some charge, Q, some positive charge, right? Well, this charge is going to be radiating an electrical field radially. And that electrical field we're going to trace all the way to the surface of this object, right? So we're just going to have some distance to the surface, right? And what's going to happen is we're going to trace out a angular direction at which this field is emanating, right? So this direction will be labeled, it's some infinitesimal amount. We know that much because we have to apply a little bit of calculus here. So this we're just going to label d phi, right? So we have d phi, boom, and we have that angle, and there's some electrical field emanating from the surface, right? So we basically have some little cross-section of this surface at which the electrical field is permeating. So outward from this surface, we have to draw our normal vector. So that is why in this case, the area is a vector. So we're kind of referencing it by its area vector that's normal to the surface, okay? So we're almost taking a chunk out of this, and it's like some little planar, and then we have our area vector. So generally you would represent this by dA. What I'm just going to do is call it ds, since that's what we named our object, right? To keep things a little less just obscure here. So ds, right? And that is our surface normal. Now, we have to represent the angle at which it leaves that surface, right? So the angle that it's going to sweep out on its path, like outwards from that surface, is going to be basically the adjacent angle that sweeps out with respect to the surface normal. So we have some angle that's subtended with respect to this charge here that ends up in this direction, right? So basically at this point we have a new angle. Okay, so we're not going to represent this angle because it's now in a different frame, and we're going to call that d theta, right? But what this is, it's essentially the magnitude of this surface normal. It's our resultant vector. So we're going to call this ds times the cosine of theta, right? Okay, we have more or less everything we need at this point. So what we need to start doing is pulling out some of our useful equations. What do we know about the electrical field due to an electric charge? Well, that's just simply E, which is equal to 1 over 4 pi epsilon naught times the charge divided by the radius squared, and then we have our unit vector, right? Okay, so we have our electric field. Where do we need to go from here? Well, let's start looking at this equation here, right? So what is this telling us? Well, we have some flux permeating the surface. We know that the flux is the dot product of the electrical field of times the area, right? So we have some d phi, right? That's going to be equal to our E dot ds, right? So that's how we're going to represent it here, okay? So we have our electric field, and let's plug in what we have, right? What we have and what we know so far about this. So obviously, we're going to have to plug in our electric field. That's just, we can't avoid that, right? So we're going to have our E, which is going to be equal to 1 over 4 pi epsilon naught, and that is going to be our charge divided by r squared. R hat, and then actually, so r hat times ds. So now we need to represent ds now, right? So we basically have what we need. We have ds cosine theta, which is our angle swept out with respect to the normal vector, and we can essentially just plug that in there, right? So we're going to rearrange it though, and it may look a little strange, but you'll see what I mean by why. So after we plug all this in, we're going to have 1 over 4 pi epsilon naught, and then we're going to have our charge, as you will. So we're gonna move that charge over above this here, above our constant, right? So we're gonna have Q, and then ds, as we basically stated, is just ds cosine theta now. So we're gonna have ds cosine of theta, right? And that is gonna be divided by r squared. And that's how we're gonna represent this for now. So, and then we have our unit vector. Okay, so now what we can do with this is take into account that whenever we have a three-dimensional object, because obviously I'm representing this in terms of a two-dimensional plane, but in reality you're going to have 3 dimensions. So there's going to be depth, and there's going to be sections of this object that you're going to have to analyze. Now, what this is, let's pull this over here. We're going to have ds cosine of theta over r squared. Okay? So, what is this? Well, this effectively is just our area swept out by the resultant vector, right? So, that is effectively our area, right? So that's going to be equal to A, right? And then we have that over r squared. Now, within a three-dimensional object, anytime you're representing the angle swept out deep within the surface itself, you can represent that by a special kind of unit that indicates the angles that are swept out from those surfaces, from within those surfaces. And this unit is generally called steradians, right? So what this is right here, in the context of a three-dimensional surface, is just 4 pi steradians, right? So this this makes sense. So obviously, if we just kind of analyze our units, it makes perfect sense. So A is what? Say meters squared. Do our dimensional analysis over meters squared. Well, that's just going to cancel out to 1. And what this inevitably ends up being is the three-dimensional analog of sweeping out an angle that you would generally see like on a unit circle, which would be 2 pi. But in this sense, since we're using 3 dimensions, this is 4 pi. Right? So 4 pi steradians. So that right now is what this is equal to. So we can plug this in for what we have right here. We can plug that in. So this is now going to be equal to Q over 4 pi times epsilon naught, and that is just 4 pi now, right? So we're going to have 4 pi times our unit vector. Well, the astute among you might already know and see what's going on here. Well, we can just cancel out these 2 factors. So we can get rid of them now. And that tells us that this equation, the flux from within a surface due to an enclosed surface, is equal to the enclosed charge, as we see here, because now this is just the enclosed charge that we're representing. So enclosed over the permittivity of free space. And that is pretty much all there is to it. Now, this gives a pretty good basis for solving for flux. Now, it's not the most useful when it comes to solving for electric field, but there is a loophole. And that loophole generally has to deal with symmetry. If you can exploit symmetry to your advantage, you can treat E as a constant if you have a uniform electrical field penetrating a surface. And if you can treat E as a constant, that makes this equation so much more simple. That means you don't have to worry about the dot product between E and A. Treat E as a constant. You don't have to do any integration. So with that in mind, we're going to represent that with the same exact problem I did in my last video, and you're going to see just how simple this is. So I'm going to clean this up, and we're going to start going through the steps. All right, so just as before, we have an electric charged rod, an infinitely long wire, and it has a uniform electrical field nestled deep within it, right? How convenient. Now, you might ask, what is this weird sort of thing enveloping your line charge? Well, it's just a hypothetical sphere. So if we're going to exploit some symmetry, we're going to treat this sphere as what's known as a Gaussian surface. And we're going to use the symmetry involved in this surface to calculate our electrical field, right? So what we can do is look and see that this right here is our radius, right? So that's just going to be R. And now the electric charges are going to radiate radially. And they're not going to have a net electric field in the parallel direction. So from beyond here, the electrical field perpendicular to the little caps here is equal to 0. And what we need to realize, so these are going to be excluded. All we really need to concern ourselves with is the length of the cylinder itself. Because there is some, if you take some kind of planar from this surface, and we're imagining as if we're dividing it into millions of infinitesimal little bits so we can get the net electric field, we're going to have some electric field from this surface. So this is going to be what we need to focus on. We're excluding the 2 caps. So in other words, say we have our Gaussian surface, right? So this, and we're going to call this part the cylinder, right? So this is going to be the cylinder portion, right? And we're going to have some electric field, which is constant, and we'll deal with that in a moment. So we're going to have E dot dA, right? So that is going to be added to our two caps, right? It's going to be added to 2 times our other 2 caps, which is just also going to be E dot dA, right? But as we've established, this cap portion is 0. That's all we need to concern ourselves with. We don't need to use this at all. All we need to concern ourselves with is the length of the cylinder itself. So, what is our line charge density equation? Well, that is just lambda is equal to the charge divided by the length, right? So, at this point, what I would suggest that we do is model this equation, but represent our charge as, in this equation, as our enclosed charge, as we have already proved, is going to be the one that's tucked deep within the surface, right? So let's rearrange this, and I like to call this the Gaussification process. We're Gaussifying, right? So we're going to bring this over. We're going to have Q now, which is our enclosed charge, equal to lambda times the length. Okay, so let's take this equation now and bring it on over, because we're going to be plugging this in for this, right? So we're going to have our closed charge, E dot dA, right, is equal to our enclosed charge divided by the permittivity of free space. So that is just going to be lambda times the length divided by epsilon naught. All right? So in this situation, as I've already stated, the electrical field is constant. So we can pull that out and just fill in what our area is. Since we're not using these portions, we're neglecting the 2 pi r squared portions. All we need to concern ourselves with is the area that's equal to 2 pi r times the length, right? The length. So we're going to have some electric field, and we're going to pull this out because we have our constant, and then this is going to be 2 pi r times the length is equal to our line charge times L over epsilon naught. Now, what we can do at this point is bring this all over, since we're treating E as a constant. So we're going to divide this all out, and we're going to end up with E is equal to lambda times L over 2 pi RL times epsilon naught. Well, as you can see here, we can cancel the lengths, get rid of those, and we're going to have E is equal to lambda over 2 pi times R epsilon naught. And lo and behold, this is exactly what we calculated before with that long, cumbersome integral using trig substitution. That was, I mean, it's kind of a nightmare. I mean, it's doable, but it's just takes time. So at this point, obviously, we just have Q over L. So that's effectively all this is, right? So maybe if I represent it this way, it'll look a little more familiar. So we just have 1 over 2 pi epsilon times lambda over R. And there it is. And that is our equation. That is Gauss's law. That is why it's amazing. It is not foolproof. I mean, What I mean is it's not a perfect sort of representation of model on everything. There will always be instances where it's just not possible. But if you can take advantage of symmetry, do it. I mean, that is that is the best option and the best bang for your buck. So with that in mind, I hope you enjoyed that. I'll have some more coming out as soon as possible. So thanks for watching.